Now let's talk about identifying unusual results. In statistics, we often need to distinguish between values that are typical or unusual from values that are usual. So usual values are values that are more than 2 standard deviations away from the mean, since within the first 2 standard deviations, we have 95% of the data. So pulse rates of adult females are normally distributed with a mean of 74 and a standard deviation of 12.5. What is the percentage of adult females with pulse rates below 49 beats per minute? So why don't I go ahead and draw my normal distribution like so. I've got a mean of 74. If I go up 1 standard deviation, I'm at 86.5. If I go up 2, I'm at 99. If I go up 3, I'm at 111.5. Now I need to go 3 standard deviations below the mean. If I go down 1 standard deviation, I'm at 61.5. 2 puts me at 49. And 3 puts me at 36.5. So what is this question asking? This question says, what % of adult females have a pulse rate below 49? So here's 49. It marks my second standard deviation. So I'm trying to find the area over here. Well, what do I know about the second standard deviation? I know that within 2 standard deviations, I have 95% of the data. So the area right here is 0.95. I know that the normal distribution is symmetric. So if I have 0.595 is the area here, the area in both of these tails is going to be 0.05. But I don't care about both tails. I care about this tail. So the area in each tail is 0.05 divided by 2 because, again, the normal curve is symmetric. So I find the area in this tail is 0.025. So 2.5% of females have a pulse rate below 49 beats per minute, right? And that would be an unusual result, right? Because it's more than 2 standard deviations below the mean, so it has a small percentage of its likelihood ability to occur. Next, in a study of facial behavior, people in a control group are timed as to the duration of eye contact that they make during a 5-minute period. Their times are normally distributed with a mean of 180 seconds and a standard deviation of 55 seconds. Let's use the 68, 95, 99.7 rule to calculate the indicated quantity. So we're going to go ahead and draw our normal distribution. That's always where you want to start. I've got a mean of 180, up 3, down 3. I always recommend making a rough little sketch. It's super helpful to make sure you've identified where your standard deviations are. So if I go up 1, that puts me at 235, 290, 345, down 125, 170, nope, not 170, just 70, and 15. So for problem number 1, I want to find the percentage of participants whose times are between 70 and 290 seconds. Well, 70 and 290 mark my second standard deviation. 2 standard deviations is going to be 95% of the data. The next thing I want to know is I want to find the percentage of times greater than 15 seconds. So I'm trying to find everything above 15. So I want to know the area of all of this in blue right here. Well, 15 marks the third standard deviation. Oops. I know within 3 standard deviations, I have 0.997 as my area because I've got 99.7% of data. I know that leaves us with 0.003% of data divided between the 2 tails. So I'm going to take 0.997 plus 0.003 divided by 2, and that's going to leave me with 0.995. 875. So I have 99.875% of data. Next, I want to find the percentage of times less than 125 seconds. 125 marks the first standard deviation. So I have 0.68% of data. I need to know how much I have left over. Well, 1 minus 0.68 is 0.32. So 0.32 is the area in my tail on the left and my tail on the right. So I need to divide that by 2. I get 0.16, so 16% of data. Last, but certainly not least, let's go back to green. I want to find the percentage of times between 70 and 180 seconds. Remember, 180 is our mean. It divides my normal distribution in half. 70 marks my second distribution. In between my first two distributions, I have 95% of data, but I want to divide that in half with my mean. So I've got 0.995 divided by 2. That gives me 0.475, so 47.5% of data.